complexities of surfaces. So definition. So I would like to study surfaces and 3 manifolds and 4 manifolds and complexities of surfaces. And so what's a good complexity of a surface? Well, the obvious notion would be genus, but I want to allow disconnected surfaces, and I want to have complexity which somehow behaves well as under gluing and taking finite covers. And then you basically know that genus is not quite the right definition. You somehow would like to work with Euler characteristic. So let sigma with components sigma 1 to sigma k be a surface. We define complexity of sigma. Well, so a good notion of complexity is Euler characteristic, but almost at least. But Euler characteristic tends to be negative. Complexity is supposed to be a non-negative number. So what you want to do is you want to take minus Euler characteristic. Then you usually end up with a positive number. But what you want to do is you want to avoid disks and spheres, because then they will have negative contribution. That's not a good notion of complexity. So what we do is we look at all components, take minus Euler characteristic, but we only look at the components which are not disks or spheres. Okay, lots of sigmas. I apologize for bad notation. So the complexity of a surface is just you take a surface, throw away disks and spheres, and then you take minus Euler characteristic. Okay, and now let n be a 3 manifold, and so all 3 manifolds shall be compact, oriented, and so on, and will be either closed or toroidal boundary. So closed or toroidal boundary. So for example, I want to allow exteriors of knots or links in S3, and let's say we have a class phi in H upper 1 of n, and then we can define what I call y of phi. So what is it supposed to be? So phi by Poincare duality is the same as an element in H lower 2 of n red boundary. So you can represent phi by an embedded surface, and you want to look at all surfaces and look at the minimal complexity of such a surface. So you look at all surfaces properly embedded in n, embedded dual to phi, and then you look at the complexity, and you take the minimum. Okay, so you know that any class in H upper 1 is dual to surface, and there's an obvious notion of complexity is to look at complexity of dual surfaces. And let's perhaps do a quick example for people who are more familiar with knot theory. So example, so let's say K in S3 is a non-trivial knot. Then if you look, let's look at the exterior. So H upper 1 of S3 minus tubular neighborhood of K. So that's just Z by Alexander duality. And let's take phi to be a generator of H upper 1. And then my y of phi is, it's easy to see that that's the same as, so what is a surface dual to phi? If you think about it, a Seifert surface for K is dual to phi, and what knot theorists very often do is they look at genus of K, meaning the minimal genus of a Seifert surface of K. And now here I look at not genus but Euler characteristic. So it turns out the correct formula is that y of phi, so the Euler characteristic here, is twice the minimal genus of a Seifert surface for K minus 1. Okay? So that's a notion which is studied in knot theory a lot of times, minimal genus of a Seifert surface. Okay, so here, minimal genus of a Seifert surface. So it turns out that y of phi has a couple of very nice properties. So properties of y. So one is if you take a phi and you multiply it by an integer, and then it turns out the complexity is a linear in n. So it's n times y of phi for any n. So it's pretty clear that there's an inequality. If you have a surface representing phi, then you take n parallel copies, and it would represent n times phi. So you have less equal, an inequality, and require a little bit of thought to see that it's actually an equality. Okay, and another nice property is that if you have two clauses, phi1 and phi2, okay, let's say you have clause phi1 and phi2 represented by surface sigma 1 and sigma 2. Now the union of sigma 1 and sigma 2 will represent phi1 plus phi2. But now, of course, here I said I want embedded surfaces. And if you take a union of sigma 1 and sigma 2, it might not be embedded, but then you do a little bit of cut and paste, which you can easily see does not change the complexity, and you get a surface which represents phi1 plus phi2. So what you get is you get an obvious inequality. Okay. So what does that do for us? So this here, so by property 1, I can extend y, which right now is defined as a map on integral cohomology, to a map on a rational cohomology. So by y, I can extend y to a map, again called y, on a rational cohomology to the non-negative rationals. And what you do, you take a rational class here, you multiply by an integer to get an integral class, then you apply your definition here, and then you divide again by your integer, and number 1 tells you that that definition makes sense. Okay, and what does 2 say, or 1 and 2? 1 and 2 say that the y is in fact a semi-norm on this vector space. Okay, y is a semi-norm on H of 1 and Q, and it turns out it actually has a name, so y is called the first norm of n. Okay. So it's really a semi-norm because it can be 0. For example, if you take a 3 torus, then any class will be represented by tori, and the complexity of tori is 0. But for example, if n is a hyperbolic 3-manifold, there are no tori, no homologically central tori, and then it actually turns out to be a norm. But okay, not something we should worry about too much. Okay, so that's very simple definition in many ways. but it turns out it has a couple of very nice properties. So what Thurston showed is following. So if you have a semi-norm or a norm, you can describe it by its norm ball. What do I mean? So you can look at all phi's such that y of phi is less or equal to 1. So that's a subset now of h upper 1. If you know that subset, you also know y. You can just recover one from the other. And well, let's just draw a picture. So just a general fact, if you have a norm or a semi-norm, and if you look at the norm ball, meaning all phi's such that the norm is less equal to 1, it's by definition a convex, well, it follows from triangular inequality that is a convex subset of your vector space. That's just an immediate consequence of triangular inequality. But what Thurston showed is that it actually has a much nicer structure, namely it turns out to be a polyhedron. So let me just draw a picture. So it's a polyhedron, something like that. Okay, that's certainly not completely obvious from the definitions why it should be a polyhedron. Okay, so not just a random convex subset, but it's a polyhedron. Okay, so far so good. Now, there's a second definition I need, namely definition. So, I say phi in h upper 1. So what's h upper 1 anyway? Has many different definitions or equivalent formulations. So you could view it also as a homomorphisms from pi 1n to z. And they say such a phi is a fiber if there exists a vibration E from n to S1. So if there exists a fiber bundle over S1, a surface bundle over S1, such that, so if I have a map from n to S1, it gives me a map from pi 1n to pi 1 of S1. So I get an induced map. And what's pi 1 of S1? That's Z. And I want that map from pi 1n to Z to be the same as a phi. So let me say it again. So I say a class phi, which I now view as a homomorphism from pi 1n to Z, is fibered if I can represent it by a vibration, by a fiber bundle over S1. Okay? And now I also want the notion for a rational class to be fibered. So phi in h of 1 and q is fibered if well, an appropriate multiple or any multiple which is an integral class is fibered. So if n phi in h up to 1 with integral coefficients is fibered. Okay. So far so good. So what does that have to do with the Thurston norm? So turns out that the Thurston proved a few more theorems. So it's easiest to explain it using a picture again. So let me just draw the same picture of the Thurston norm ball. And so that's a subset in H upper 1 and Q. And in here I can consider, why not, all of these which are fibered. Okay, so it's just some subset of H upper 1. And a priori it's some random subset. Now, let's say we have a phi here, which is fibered. Now, what is pretty obvious is that the set of fibered clauses is a cone. So if that fellow is fibered, then everybody here on the cone also has to be fibered. And what requires a little bit of thought, but it's not so difficult, is to show this set of fibered clauses as an open set. So it's really an open cone. So here's like a cone like that. So this is open cone. So openness is in some sense not so terribly difficult to show. It's something which also holds in more general setups. But what the interesting bit is, what the Thurston proved is that these are cones, and these are cones which are cones on top dimensional faces of the Thurston norm ball. Meaning, if you have a phi here, then the whole cone on the corresponding face has to be fibered. Okay? So that's quite amazing. So if you found one fibered guy, then everybody in the same cone has to be fibered. Okay? So open union, open cones on top dimensional faces of the Thurston norm ball. Okay, so you get a picture like that. Because now I'm somewhat challenged. And also an important point is, so it's cones on top dimensional faces of the Thurston norm ball, which means in particular you cannot lie on the cone on a lower dimensional face. So for example, you cannot lie on the cone of this vertex. Okay? Okay, so that's a really nice picture how this complexity of surfaces talks to fibered clauses. So it's, I guess for Thurston it ranks as achievement number 37 in his long list, but even that is already a beautiful observation theorem. Okay, and now what we'd like to do is one would like to determine, figure out what is the Thurston norm for given 3-manifold, and you would like to know what are the fibered clauses of fibered 3-manifold. Okay, so if you took some knot theory, the corresponding question is, given knot K, how can you determine the genus of a knot K, and how can you determine whether a knot is fibered or not? And perhaps some of you, or many of you, will have read Rolfsen, and then you know that the good old Alexander polynomial has something to say about genus and fiberedness. So let me recall the definition of the Alexander polynomial. So I will use it slightly. So the Alexander polynomial for knots has about 27 different definitions, and some are more helpful than others. And I will use the one I like best, which also immediately generalizes to 3 manifolds. So let me give you the definition for 3 manifolds in general. So let M be a 3 manifold, and by F I denote H1 of N divided by torsion. Okay, so it's just the torsion free part, if you want, of homology, so it's a free abelian group. And then we consider H1 of N with ZF coefficients. So what do I mean by that? So let's twist in homology, and it's really just very naive. It's just H1 of the F-fold cover of N. So it's H1 of the F cover of N. Put differently, it's the universal torsion-free abelian cover of N. But you see, if you just look at its homology, it's sort of a monster. It's an infinitely generated abelian group in general. That's not so good. But the interesting bit is that the deck transformation group is acting on it. So that is really a module over ZF. So it has some structure. And now we define the Alexander polynomial of N to be the order of that module, which is an element in ZF. Okay, so what do I mean by order? It's best described by a brutal example. So it's easiest if you just forget everything you ever learned in algebra, then I can give you a definition. So what do I mean? So e.g., if let's just pretend for argument's sake that ZF is a PID. So if this here is a sum of cyclic modules, then the Alexander polynomial is just the product of the PIs. Okay, in general it's not a sum of cyclic modules, but we don't care right now. So the order, or what they called here, so it's called the Alexander polynomial N is, if you want, a measure of complexity of the Alexander module. And the real definition is a little bit more tricky. It has to take a resolution and GCTs of minus and whatnot, but that basically gives you the idea. Let's pretend it is a sum of cyclic modules, and then it's just the product of these guys here. And if that sounds scary, so let's do an example. So, for example, if you take L and S3 a link, then I can again consider the manifold which is given by looking at the exterior of the link. So nu always means an open tubular neighborhood. And if I do that construction here, what I get is the ordinary Alexander polynomial, or multivariable Alexander polynomial of a link. So it's delta L, so it's multi-variable Alexander polynomial of L. Okay, in particular if it's not, you get the good old Alexander polynomial of a knot K. And you have seen perhaps different definition of the Alexander polynomial, but it's equivalent to that definition. Okay. Okay, so perhaps a little bit scary here, but for links it's really just an object that you hopefully have seen before. Okay, so what does that have to do with the problem of determining the genus of a knot or the first norm? So one of the theorems which every knot theory course should at least cover is the following. So it's a classical theorem. So let K in S3 be a knot. So we write so delta of K. So let's see, what is it? So I said it's an element in the group ring of H1 modulo torsion. What's H1 of a knot complement? That's just a Z. So you don't just get the group ring of a Z. What's the group ring of Z? Well, that's Laurent polynomials. So I can use this Alexander polynomial as a Laurent polynomial. And then when you get this, that the genus of K remember that's the minimal genus of a Seifert surface of a surface bounding to knot K. So twice the genus is greater or equal than the degree of the Alexander polynomial. Okay, you look at the Alexander polynomial, and by degree I mean difference between the highest non-trivial coefficient and lowest non-trivial coefficient, and its degree gives you at least a lower bound on the genus. Okay, so better than nothing. And the proof is not so terribly hard. So perhaps the easiest is if you switch to a different definition of the Alexander polynomial. For example, you can determine the Alexander polynomial in terms of Seifert matrices, which again come from Seifert surfaces, and then it's very simple to see that that's a lower bound on the genus. Okay, or a different way of seeing it is, well, what do you do here? So here we said we look at the intrinsically covering, and its homology, and you can study the intrinsically covering of a knot just by taking a knot exterior, cut along a Seifert surface, and then you somehow glue infinitely many copies together, and then you can express the homology of the intrinsically covering more or less in terms of H1 from the Seifert surface. So that's really not so terribly hard. And another fact is also quite useful. So if K is fibered, then the Alexander polynomial is monic. So that just means that the top coefficient is plus or minus 1. And more interesting for the remainder of the talk is that the degree of the Alexander polynomial is precisely twice the genus. Okay, and why is that? So it turns out if it's a fibered knot, then the Alexander polynomial is nothing but the characteristic polynomial of the monodromy on H1. Okay, fibered knot just means it's a surface bundle over S1, so you have a monodromy on the surface, and what's fairly simple to see is that the Alexander polynomial is the characteristic polynomial of the action of the monodromy on H1 of the surface, of the fiber surface. Okay. Okay, so the Alexander polynomial gives you the genus in the fibered case. In general, it gives you a lower bound, but it certainly in general will not give you an equality. So for example, there are many knots where the Alexander polynomial is 1, which means the degree is 0, but where the genus can be arbitrarily large. Okay, so Alexander polynomial has some information, but certainly not full information. Okay, so Lavi, what can you do? Okay, any questions? Okay, so that's the setup for knots. Now I'm sort of studying a more general setup, namely I look at the first norm of a 3-manifold, and it turns out there's a very similar theorem, which is not much harder to prove. So, theorem. So, oddly enough, it goes back to McMullen. He was the first one to write down. For him, it must be achievement number 157 on his list, but it's still kind of useful. So let n be a 3-manifold, and so I get the Alexander polynomial. So I said it's an element in the group ring of H1 modulo torsion. So what's an element in what's in the group ring? Well, it just means it's a formal sum of elements in F. So you can write it as follows: A G times G, where G is lying in F. Okay, let me just write it like that. And now, given phi in H upper 1 of n, so H upper 1 of n has many reincarnations. One is it's the same as homomorphisms from H1n, H lower 1n to Z, but then any map from H lower 1 to Z has to factor through H1 modulo torsion, so that's the same as homomorphisms from F to, actually I want to allow rational coefficients for Q. We define what I call A of phi. So what's A of phi? What is A of phi? A of phi is, so let me perhaps draw a picture, whether you like it or not. So think here of F. What's F? F is a free-wheeling group. So let's say B1 equal to 2, it's just Z2. And then for the polynomial, you can write down the Newton polygon. Newton polygon just means well, you basically put a dot wherever one of the coefficients is non-zero. So you get some picture like that. It's again going to be symmetric. Okay, some picture like that. So here the dots correspond to coefficients which are non-zero. And now you have a phi. So a phi, well, sort of a dual to F. And what is A of phi? A of phi is the thickness of this picture in direction of phi. So what do I mean? So that's the same as saying I look at, I maximize, sorry, 2A's is bad. Let me write C here. So I maximize phi G minus phi H, where G and H correspond to non-trivial coefficients. So C G not equal to 0, C H not equal to 0. Okay, so you could say a phi is a measure, a distance measure on F, and I define A of phi to be the maximal thickness of the Newton polygon here. And then what you get is that A of phi is a lower bound on the first norm, and it's an equality for the quasi-fibered phi. I have to tell you what I mean by quasi-fibered. So, definition, phi is quasi-fibered. So by quasi-fibered I mean that phi lies in the closure of these fibered cones. So phi is quasi-fibered, phi lies on the, or in the closure of a fibered cone. Okay, what is going on? So with this here sounds a little bit obscure perhaps. Let's go back a second. Let's consider the case where B1 equals 1. Okay? So where f is just a z, so for example not complement, and then A of phi is just a very complicated way of saying I take the degree of the Alexander polynomial. Like if you take the Alexander polynomial and it's just one variable case, and you write down the non-zero coefficients, what's the thickness of what you see? Well, it's the degree of the Alexander polynomial. So A of phi, what looks so complicated here in the one-dimensional case, is nothing but the degree of the Alexander polynomial. And so that A of phi is a lower bound of the first norm is just generalization of statement number 1. Now, so let's now first look, let's forget about quasi for a second. So if I have fibered clause, then you get an equality here, and the reason is exactly the same as for knots. Somehow you just do it, it's not so terribly complicated. So for fibered clauses you get equality, and the reason is exactly the same as for knots. Now quasi-fibered is slightly more general. So I said fibered clauses form an open cone, but for quasi-fibered also allow the clauses which sit on the boundary of the fibered cones. And why do you get equality for the clauses on the boundary? Well, because A and Y are continuous maps. So if they agree on this open set here, they also have to agree on the boundary of the open set. Okay, so stupid little point that actually very helpful. Okay, any questions? Okay, so the Alexander polynomial for 3 manifolds gives you partial information, very nice, but certainly doesn't give you full information. Now, fortunately, when you deal with 3 manifolds, there are many more techniques. So the various techniques how you can really determine the first known fibered clause of a 3 manifold, at least if you have a good computer. So can determine why using, so for example you can use this Hegel-Fleuromology. So whatever that means, Hegel-Fleuromology is sort of the big brother of the Alexander polynomial. It sort of sits on top of the Alexander polynomial and knows more than it, and it actually knows the first norm. And for knots, there's log fluorology, then some flavor, which I never quite know. Or you can use more traditional methods. I guess you can somehow use the normal surface methods due to I think Cooper and Stefan Friedl wrote some algorithms. So there are various ways of doing it. At least if you have lots of time and a good computer. But as a problem, it's basically a solved problem. If you have a three-manifold, you can figure out the Thurston norm. Okay. So far, so good. Now. Let's go to four manifolds. So, in some sense, you can play a very similar game for four manifolds. Namely, definition. Well, let W be well. Let me not the W. I want N. Sorry. Let M be, now I want to restrict to closed four manifolds. You can also do it with manifold boundary, but just to closed four manifolds. And let's say you have a class C in now H upper 2 of M, same as H lower 2 of M. Then you can define a complexity exactly the same way as we introduced the Thurston norm. So you can define, now I call it X of C. Well, it's exactly the same definition, so you minimize the complexity of surfaces where sigma is embedded in M dual to C. Okay? And okay, you have to think for a few minutes why you can always find a surface, but you can do so, and then you can do exactly the same definition. You just minimize complexity over all surfaces. Okay. So that is a very difficult problem. If you have a four manifold and you would like to know what's the minimum complexity of surfaces, well, good luck. So that's certainly like basically any question you ask about the smooth four manifolds. It's usually impossible to answer. So let's perhaps look at a special case. Namely, what I would like to consider is the case where M is S1 times a three-manifold. Okay, so consider.
So are you assuming the embedding is smooth?
Yes, so smooth four manifolds, yes, and smoothly embedded. So yeah, I work in the smooth category. Yeah, good question, yes. So consider the case M equal S1 times a three-manifold. So let's just see what we can do. So let's pick a class C. So take C in H, what I say is switch lower, doesn't matter, 2 of M. So that's a C, and that's an inverted, included symbol in case you get confused. So by Kenneth, you can just write that. So H2 of M is basically H1 of M times with a Z plus H2 of M. So I can write it as well, gamma times 1 plus phi, where a gamma is in H lower 1 of n and the phi is in H lower 2 of n. Okay, that's just a Kenneth decomposition. And now let's just try to produce a surface representing C out of what's given over there. So okay, so let's take a curve which represents gamma. So let gamma E represented by C, and let's take a surface in M representing phi, so phi shall be represented by sigma. Then we want a surface which represents sub C. Consider, well, what I can do is I can look at C times S1 union sigma. Okay, that is a surface in S1 times N. And basically Kuhn says that this here represents my original class of C. Okay. So represents C. But now you see we have a problem. Namely, what we really want is we want an embedded surface. But my curve C might well intersect my surface sigma. So as it stands, it's not going to be embedded. So where are the problems? The problems all come from the intersection points of C with sigma. And what you want to do is you want to remove these intersection points. And what you do is, so each intersection point, well, you have sort of an two disk intersecting a two disk. What you can do is you remove the two disks and you can glue in an annulus. So remove intersection points of C sigma and glue in annuli. So it requires a bit of thought perhaps why this makes sense, but for each intersection point you take out two disks on the two sheets and you glue in an annulus, and what you found is an embedded surface. Okay, but now you are paying a price for it, namely you changed the complexity of the surface. So then so what I get is, so I call it my complexity of C. So I now found an embedded representative, and let's see what we can say about it. So this here is less or equal than the complexity of that surface. What's the complexity? So well, here there's no contribution, that's just tori. Here, when for sigma I can do the best optimal case would be to take a sigma which is first norm minimizing in N. So I take, so I can arrange that to be less equal than y of phi. So you should have, so x corresponds to M4 and y corresponds to M3. So mx and y, that's how you're supposed to remember it. But now here you pay the price. And what did you do? What you're doing in annuli doesn't do any harm. But what you did do is you remove the disks. But since we take minus all the characteristic, you really increased the complexity. So what you did is, so for each intersection point, you you gained you added 2 to the complexity. So plus 2c dot well, I should write like that. C is number of intersection points of C and sigma. Okay, so that's sort of if you think about how to construct surfaces representing homology clauses, that's what you're basically forced to do. So what is that? Yeah, that's a little bit annoying. So let me just be a little bit vague. So in many cases, but not in all cases, so that's the geometrical section number. So in many cases, but not in all cases, that is nothing but you can arrange it to be the algebraic section number. And what is that? That actually turns out to be nothing but the self-intersection number of my class sub C. If you think about what's a section product on your 4 manifold S1 has a 3 manifold, that's what you get. Okay, so here I'm being a little bit vague, but what can I do? So in many cases, you get that XC is less or equal than y of the corresponding phi in the 3 manifold plus the self-intersection of perhaps that's through I presume that, yeah, I guess the two got lost somewhere. Anyway, so in many cases, but not all cases, you can basically find a surface which has that property here.
So I cannot understand what's your operation there. So that suppose there's only one intersection between the C and sigma. What did you do that?
So we basically have so that's your local picture.
Yeah.
And then you remove a disk here.
Yeah.
You remove a disk on that sheet, and you glue in an annulus. It's like a hot film.
Okay.
Okay. So in many cases, you basically get that upper bound on the complexity of surfaces in S1 of the 3 manifold. So what about the lower bounds? So when you deal with 4 manifolds, you certainly have not so many choices or not so many invariants left. And in some sense, the only non-trivial invariant which is left are subgrid invariants. And subgrid invariants conveniently give you lower bounds on the complexity of surfaces. And what we get is, so using Seiberg-Witten invariance and junction equality of Tronheim-Mrovka and whatnot, we get that you get a lower bound on the complexity, and in our particular case, the lower bound turns out to be, so you get this is square term here, and then you get another term, and it turns out to be what I called A of phi beforehand. And the point is basically you have subgrid invariance, it's the only thing we have, and subgrid invariance for S1 times a 3 manifold, or basically just the Alexander polynomial of a 3 manifold, and if you go through your isomorphisms, that's what you get. Okay, so for 4 manifolds, the only thing you have is this lower bound. The lower bound, which in 3 manifolds corresponds to the Alexander polynomial. But there are no bigger brothers yet of subgrid invariance. There's no Higgard, Fleur, whatever. That's what you get. Okay, and so here there's clearly a discrepancy. You can just take like S1 times 0 frame surgery on a knot, and you immediately get discrepancy between the upper bound and the lower bound. Okay, and the theorem which is joint work with my long-term collaborator Stefan Friedl, that so if n is irreducible then with exactly the same notation as over there, the complexity of C is greater or equal than y, so that's the point, of phi plus c squared. Okay, so we can prove the lower bound from what's corresponding to Alexander polynomial to the first norm, meaning that in most cases, yes, in many cases, we can in fact determine the complexity. Okay, so equality in many slash depending on taste, most cases by this result here. So two remarks. So it turns out that theorem was actually proved by Kronheimer in the late 90s using some fancy invariant which I don't understand. So proved by Kronheimer in 1999 using a thing that I call the monopole classes, whatever that means. So now you wonder, so what am I doing here? So what we can also do is we can also deal with the case of S1 bands over 3 manifold, which Kronheimer cannot do, but which are technically a little bit more difficult to explain. So that's why I stuck with them S1 and the 3 manifold. But so we can also do it gets a little bit more technical, but almost to say also for S1 bundles over N. Okay, so what's the key idea? So the key idea is to use the wonderful stuff, wonderful results given to us by Danny Weiss, Pschititsky Weiss, and Ian Agel. And so let me just very quickly state what they proved. So theorem, and so that's due to Ian Agel and Pschititsky Weiss, and in fact, in many cases we need due to y. So if you don't know Pschititsky yet, so there are two Pschititskys, one has to be careful. There's a Joseph Pschititsky, an knot theorist, and there's a very clever nephew called Piotr Pschititsky. And what they proved is the following. So same assumptions. So n irreducible and not a graph manifold. And now let's say we have a class phi in H upper 1 not fiber. Oh, I should say, I forgot to say, this here is an equality if that class happens to be a quasi-fiber. Okay, so it's sort of the same, I would decide this before. Inequality, but an equality in that class it happens to be quasi-fibered. And so the theorem says, so if you have an irreducible 3 manifold and it's not a graph manifold, and now let's say you have a non-fibered class. And for non-fibered classes we're sort of out of luck at the moment. And now you can ask me, perhaps if I go to a finite cover, perhaps I can make it fibered in a finite cover. But now requires a little bit of thought, but that's actually, turns out it's impossible. If you have a fibered class, if you have a non-fibered class in a 3 manifold, you cannot promote it to a fibered class in a finite cover. But the miracle is that you can make it as almost as fibered as it gets, namely then there exists a finite cover P of n tilde to n such that the pullback of my non-fibered class phi, so I said it's not fibered, cannot be fibered, but you can make it quasi-fibered. Okay, and so that's basically the famous virtual fibering theorem for hyperbolic 3 manifolds, but now with Chuditsky-Weiss it also works for non-graph manifolds. And I mean, the virtual fibering theorem is well, famous for good reasons, but in some sense what Ian proved, well, together with the other guys in some sense, is a significantly better statement. So if you have a 3 manifold and you know it virtually fibers, well, you could say, so what? I mean, just some random fibering upstairs, who cares? But the beautiful thing is, which is perhaps underappreciated a little bit, is that the statement is so much more clever. It says you start downstairs at your 3 manifold and you have a class phi which you're really interested in. And then what these wonderful authors give you is a finite cover such that the guy you're interested in, one case of a 3 manifold is technically harder, but the idea is really just we use this wonderful theorem and then use that upstairs in the 4 manifold you get an equality. Okay, thank you.